Good morning, everyone. Our session is about science to solution. So we have a huge responsibility here to discuss this. And I've sent the speakers some quite interesting questions. So let's hope if they take up the challenge. Our first speaker this morning is Professor Tandong Yao. And we'll speak about glacier melt that causes imbalance of Asian water tower in a warming climate.
Good morning, everyone. Thank you very much for gathering in the morning. And my name is Shin Sugiyama, President of International Glaciological Society. And I'm very glad to share this moment to present the Seligman Crystal of International Glaciological Society to Professor Yao Tandong. The Seligman Crystal, which is here, this is, I would say, the most prestigious award in the field of glacial research. Everyone in this field, something dream about this. And this is the award in recognition of outstanding scientific contribution to glaciology. And this crystal is established in 1963 after the name of the founder of IGS. So it's about 60 years history of this. So I have a citation to read for him, so give me some time for this. Dr. Yao Tandong from Institute of Tibetan Plateau Research, Chinese Academy of Science, has played a leading role in the international community in the field of climate and ice core research. He has initiated foundational work in Tibetan Plateau climate reconstruction from ice cores and glacier fluctuations, as well as research in environmental change and its impact on the Tibetan Plateau and surrounding regions. One of Dr. Yao's most influential areas of research has been his exceptional contributions that advanced understanding of the response of glaciers to climate change on the Tibetan Plateau and the surrounding regions. His pioneering work includes interpretation of stable isotopes of oxygen and hydrogen in ice cores and precipitation across the Tibetan Plateau. For example, Dr. Yao initiated in situ glacier mass balance measurements on the Tibetan Plateau that provide unprecedented information about the heterogeneity of mass changes in the region. He also demonstrated that a significant relationship exists between these isotopes in precipitation collected across the northern Tibetan Plateau and air temperature, one of the first such correlation established outside the polar regions. He further identified abrupt climate changes in this tropical subtropical region on different timescales, including transitions from glacial to interglacial stages. Dr. Yao's contributions include influential leadership in conducting innovative and cross-disciplinary pioneering research by organizing international groups. He was the founder of the Institute of Tibetan Plateau Research, Chinese Academy of Science in the 2000s, and he has served as the director of the Institute for the past 15 years and has served as co-chair of the Third Pole Environment Program since 2009, addressing water, ice, air, vegetation, rock, human interactions in the Third Pole region. Dr. Yao's remarkable contributions to the field of glaciology, climatology, and environmental change across the Third Pole have been invaluable in assessing the impact of the recent anthropogenic influences in this critical but historically understudied region. Dr. Yao has played a seminal role in bringing international attention to what remain one of the most difficult to access and least studied regions of the world. On behalf of the award committee of the International Glaciological Society, congratulations.
Dear colleagues, dear friends, ladies and gentlemen, it's my exciting moment to receive the Crystal Award. And thank you so much, Shin, to give me the award, and also my appreciation to IGS to give me a Crystal Award, and also the CliC conference to give me an opportunity to receive the Crystal Award. It's also my great pleasure to give the presentation about the third pole glacial melt and Asian water imbalance. Third pole is Tibetan Plateau and its surroundings, also called the Asian water tower, with the largest ice mass outside the polar regions. So Asian water tower is the most important water tower in the world. There are 78 water towers in the world, and 16 exist in the third pole region. Provide water resources to some people say it's 2, some people say it's 3 billion people, including China and India, the largest population in the world. And Asian water tower is composed of different water bodies, including glaciers, which is about 100,000 square kilometers, permafrost, about 1.3 million square kilometers, snow cover, about 300,000 square kilometers, and the lakes, about 50,000 square kilometers, and the rivers, which is origin about 13 to 16 rivers, including Yangtze River, Yellow River, Ganges, the Indus River, etc. Asian water tower stores huge water in the downstream rivers, including glaciers, lakes, and rivers. We observed different lakes, different glaciers, and different rivers, and then used the model to calculate how much water stored in the glacier, lake, river, and with a total of 10,000 gigaton, which is more than 200 years annual discharge of the Yellow River. So think of that, we have a very high confidence about the water resources stored in this region for the human society. And the Asian water tower composed of endorheic and exorheic basins, which regulate the Asian water tower changes with the interaction between the Indian monsoon and the westerlies. And what is happening is a rapid climate change or warming in this region. It's the temperature increase rate is about twice as large as the global average. Actually, after the 1990s, the increasing of temperature is 0.44% per decade. Think about global average is around 0.2 per decade. So we focus on scientific questions in this region. For example, how did westerly Indian monsoon interaction and climate warming affect Asian water tower changes? What changes in Earth system process will be triggered by changes in different water bodies in the Asian water tower? What are the characteristics of large-scale telecollections associated with changes in the Asian water tower? After many years study, we found that cryosphere area in this region substantially decreased, largest decrease in the southeastern part, and then decreases toward the interior, and to the very northwestern part, actually, some glaciers are still in a positive mass balance. Some people call it extreme phenomena in this region, called Karakoram anomaly. So in the blue color, actually you see the mass balance in the Antarctic region, and the red color shows mass balance in the exotic region. And you see much more substantial negative mass balance compared to the Antarctic region. So the imbalanced water distribution also shows the very various changes in precipitation. And actually in the Antarctic part, you have increased precipitation, which is associated with wetness. And in the exotic basins, you'll see the decreased trend of precipitation associated with the Indian monsoon. So generally speaking, the Asian water tower imbalance is characterized by accelerating transformation from solid water to liquid water. Talking about glaciers, it's decreased from 100,000 square kilometers to now less than 8,000 square kilometers. Different numbers, different calculations, but it's much less than 90,000 square kilometers. And 1.3 million permafrost decreasing from 1.3 million square kilometer to 420 square kilometer, 2,000 square kilometer. And permafrost, the last one is snow cover. And permafrost decreasing from 1.5 million square kilometer to 1.26 million square kilometer. And at the same time, liquid water increasing, lake volume increasing from 6,100 cubic water kilometer to 9,000 cubic kilometer. And runoff at mountain outlets increased from 5,500 cubic kilometer to 6,500 cubic kilometer. Then you have very serious hazards associated with the imbalance of the Asian water tower, including glacial lake runoff, glacial lake outburst flood, ice collapse, and some other consequences associated with these disasters. And the most threatening process is ice collapse, and nature had a special comment about what is happening and what will be most influential in the future for the human society. And Asian water tower imbalance will further intensify in the future. We had some projections about glaciers, about the lake, about the river. They all show very different substantial changes. Glacial volume will decreasing. Some numbers show 70%, some numbers shows 60%, but anyway, it's close to disappearance. And the lakes at the end of the century, lakes and rivers are generally increasing. Lakes will substantially increasing, and the rivers, different behaviors, but generally speaking, they all increasing. And future climate warming will exacerbate the imbalance and result in a liquid water dominant third pole. So that means we have more water in the future in this region, but much less solid water. So glacial lake outburst and glacial collapse risk is expected to almost triple in the future in the region. So that's why we had an international effort to deal about issues scientifically, and this is called the third pole environment, as our IGS president introduced. And we call that TPE. We have the scientists worldwide to have a steering committee to organize scientists worldwide. And scientists in the world come from institutions, universities, companies, and also intergovernmental agencies. And we had so far 10 workshops. The last workshop was in 2023. The same year, I had an award of Crystal, and because of COVID, the award was delayed until today. But we had 800 scientists worldwide to talk about third pole environment change. The cryosphere change is one of the most focused topic. And based on that discussion in the conference, also associated with the running UNESCO program or action called Cryosphere Decade or something very similar program, pronunciation, I mean. We are now developing another topic for TPE, third pole glacial melt and Earth system adaptation, simply called TPGE. So TPGE aims to better understand glacial dynamics and its impacts on climate change, water resources, and ecosystem, and to better support regional and global sustainability in the ice vanishing third pole. We are talking about 5 tasks, but it's still developing and finalized. The task 1 is glacial monitoring, and task 2, ice atmosphere interaction and transformation. The 3rd, Earth system observatory and early warning platform. Task 4, development of next generation modeling with AI support. And task 5, glacial melt adaptation with technology innovation. And for the task 1, glacial monitoring, we have already established 35 to 40 mass balance measurement sites in this region. And we have also used most developed balloon to observe from sky. And we have selected the most challenging but most interest sites, Amherst, Zhuoyu, Xixiangbamba, to see what are the changes for ice at the extremely high elevations. And this is what the station look like. Started from 5,200 to 8,830 meters. That means the summit. It's there's low rock, so you cannot hold the ropes on the at the very top. 8,840 something, but it's 30 meters, so close, very close to the summit. And also, we tried very hard to resolve the challenges to maintain the observation network up to the summit. So what we did is we trained the mountaineers as a technician. We spent some years to do that, but it was successful. So they go there every year, and they will do that for the maintenance. And also collection the gradient slow ice samples and ice cores from 6,500 to 8,848 meters. Task 2, ice atmosphere interaction and transformation. Of course, we used the traditional way of automatic weather station, which really used in the Andes Mountains. And now we are using this for the Tibetan Plateau and the Asian Water Tower. And also use the drones and the satellite images, of course. And of course, very recent developed the balloons, which is very efficient. Gojin is doing that, and she was discussing that with Ray yesterday. I've got observation platforms to monitor water carbon changes through the troposphere. That also very recently developed in this region, and we hope that can be further developed in the future. Task 3 are system observatory and early warning platforms. Wei Caiwan is here, and he presented his results the day before yesterday, I think. We have the Lhasa River Earth System Observatory, which is running by Bao Sheng. He's also here. And we have one station for ice collapse. Once ice collapse happen, it will be automatically signals to the society, to the local people, and they have time to escape at least. And then the glacial lake outburst flood, also a station between China and Nepal. And they are the largest lake and with the most serious disasters in the future several times. Now we have the observatories in this, beside this lake. Task 4, development of next generation modeling with AI support. And Ray has done for so many years, but okay, we think it's very important for this region. And also with the cooperation of meteorologists, we are collecting the changes in the Asian Water Tower with the global or regional telecollections. Text 5, for glacial melt adaptation with technology innovation. We have the artificial snowmaking and nano material cover to compare what some other methods, approaches, to compare what is most efficient way if it can be done in the future. Of course, constructing ice cores from glaciers, we are observing with the best balance. And then, based on all these activities, we think it's another International Association for Trans-Himalaya Earth System Science, simply called ATH. It's also important for scientists worldwide. That is still organized by Shilong Piao. He is now the vice president of Peking University. And for the future collaboration, we are developing a global campaign for Decade of Action for Cross-Field Sciences, organized by UNESCO, and focus on glacial melt and Earth system adaptation of the Asian Water Tower. We are planning to organize a TPG conference. I talked with Ray, with our new Secretary General, Alan, for IGS, and also with UNESCO, Anil, who is organizing Cross-Field Decade. And also, we are discussing with other international organizations and programs. And we think it is very important to have such a meeting in the future. In the Tibetan Plateau, Lhasa, for example, or somewhere in this region. Thank you very much.
Perfect, thank you very much. Great talk. So the next speaker is Richard Levy, that will talk about coastal impacts.
Tēnā koutou katoa, ngā mihi nui ki a tātou katoa. Thanks very much to all of you for coming along to the Science to Solutions session this morning on the last day of the conference. I really do appreciate the opportunity to share with you some of the research I've been doing over the past several years with a team of many in an effort to try to connect the work we do in Antarctica to the people of Aotearoa, New Zealand. Now, presenting on the final day of the conference gives me the advantage of having listened to and learned from many of the outstanding presentations that have been delivered over the past several days. And I was particularly impressed by the storytellers who presented in yesterday's plenary and the way that they used beautiful imagery to support their narratives. And I didn't see a graph in any of the presentations. And it sort of reminds me that we, as scientists, often utilize graphs to try to communicate our knowledge to people who need to use our science, and that's not also always necessarily the most effective tool. So I'm going to try to use some visuals to tell my story today, but I will acknowledge, and I realized as I went through my talk, that there are plenty of graphs still spread throughout. So it's something for us to think about. What are more effective ways to communicate our science so we actually are getting our science to help with solutions? Now, this first image I have up here is taken from the Freeze Hills in the Transantarctic Mountains, looking towards the East Antarctic ice sheet. And it's really here just to prompt me to back up a little bit and provide some context to set the scene for the story I'm about to tell, and sort of help you understand how I've got to the point where I'm really trying to bring with my colleagues the science we're doing in Antarctica to bear on solutions. Now, I've spent much of my career studying the Antarctic geological history and using those histories to help us understand how climate has interacted with the ice sheets, causing it to grow bigger and shrink across millennia. I've worked with modelers to help us try to understand the processes that drive the ice sheet, both in the past but also into the future, to help us understand how the ice sheet will respond as the climate continues to warm. And so, yeah, really much of my career has been focused on Antarctica. And a number of years ago, I was working in this rather stunning place in the Freeze Hills with Tim Naish, who was a key player in the story I'm telling. And Tim and I were sleeping together in a tent, as many of us do in Antarctica. And Tim turned to me and said, "Hey, Rich, does all of this work that we're doing really make a difference? Does it matter?" That's quite a confronting question to be asked when you're sitting in a very cold environment, working really hard to try to get these records to help us understand Antarctica. But it was a really important question, really philosophical question, and it got us all thinking about, okay, so what can we do to do a better job of taking what we're learning in Antarctica and bringing it to the world? How do we connect the work that we're doing in the Deep South to communities in Aotearoa, New Zealand? And here's just a picture just to highlight the real reason why we're worried about what's happening down in Antarctica and across the cryosphere in general. This is a pretty typical scene. This is a photograph taken from Mount Victoria looking across Wellington Harbour, and lots of infrastructure, people living right next to the coast are obviously going to be impacted by change in Antarctica. Now, here's my first graph. Tim and I, of course, aren't the first to think about this and recognise this need. And there have been many colleagues in New Zealand and around the world who have been trying to do this sort of work for a long time. And New Zealand is relatively advanced in terms of trying to get science to solutions, particularly around sea level. And our government produced in 2017 this really important document, Coastal Hazards Guidance Document, and included in it sea level rise scenarios based on IPCC projections, and provided pretty clear guidance to our planners, coastal communities, that they should be using these sea level projections as they plan for the future. But there was a clear acknowledgement in this guidance that local factors weren't considered in these projections, things like the ups and downs of the ground in response to a range of processes. Local factors matter, but they weren't incorporated in these projections. One size simply does not fit all when it comes to sea level. So Tim and I created, constructed, developed a couple of fairly major research programs, NZC Rise, Te Taipari o Aotearoa and Te Ahurihuri Te Aho, Our Changing Coast, and in conjunction with the New Zealand Antarctic Science Platform, really worked to try to improve our ability to project sea level for Aotearoa. Now, of course, one of the key things we are all very well aware of in this audience is there is a need to continue to try to reduce uncertainties in ice sheet and glacier contribution to sea level rise. And I attended a session on the first day of the conference and saw some amazing talks of from people doing some excellent work on trying to really deal with improving our ability to understand how the ice sheets and glaciers will respond to warming. And just to acknowledge a few here, Peter Su, who is involved in our sea level research, has been doing some pretty remarkable work with emulators, as have many other people. But some other talks that I heard, really doing some remarkable work that we need to continue doing as we try to improve our ability to project future sea level rise. But two things that were stated in this session jumped out to me. The fact that we're committed to ice sheet and glacier mass loss, even if we stop warming today. That message came across very clearly. So, we are committed. There's nothing we can do even if we stop warming today. But there is still high scenario dependence. And again, what we do now to minimize our emissions really matters. So those messages need to be propagated to people who are looking for solutions. So while that ice sheet work continues, if we start getting down to the local level, we've been putting a lot of effort into understanding vertical land motion. And it's really important to understand what our coasts are doing because it can affect the rate and magnitude of sea level rise, sometimes exacerbating or mitigating the amount of sea level rise depending on where you are. In areas where the land is going up, it decreases local sea level rise, and in areas where the land is going down, it increases local sea level rise. So getting a handle on this is really important. And in Aotearoa, New Zealand, it's particularly important because we straddle a plate boundary, and the plate tectonic motions cause our coasts to go down in some regions and up in other regions. So knowing what's happening is really important from a local perspective. You can also cause land to sink by extracting water from the ground. And that's another factor to consider. But also, putting cities or large buildings on the land can cause the land to sink and exacerbate sea level rise. So getting a handle on what's happening around the country with respect to vertical land motion really matters. And in order for us to do this, geodetic data are a critical resource. Not only are they incredibly valuable in helping us understand what's happening in terms of mass change in Antarctica and Greenland, they also provide us this ability to know what's happening right now on the land in which we stand. And I've got an example here from the Wellington GPSS that's connected to or correlated to our tide gauge here in Wellington Harbour. The image on the top there is of Te Papa across the road, and that's where this GNSS system sits. And the green line is a record from that GNSS over the last 20 or so years, showing a fairly consistent trend down up until about 2017. So the land's been subsiding about 3 millimetres per year. That's equal to the rate of, almost equal to the rate of global sea level rise, so doubling the rate of sea level rise. But in 2017, we had an earthquake in Kaikoura. The land popped up slightly, and the motion has been relatively stable since then. So these time series allow us to understand what the land is doing right now. We also use satellite INSAR data, radar based on the Sentinel and previously the Invisat platform can actually send radar beams down to Earth, back to the satellite, and can measure changes in the height of the Earth's surface at millimetre scale. So combining GNSS and GPSS together gives us a good sense of what's happening around our coastal margin. We pulled all of this information together a few years ago now and produced these maps that you can access on the web. You can go into the coastline and click on a location every 2 kilometres around the New Zealand coastline and pull up sea level projections like the one you see here. And the key point is that you can consider global sea level, climate-driven global sea level rise. That dashed line is SSP 4.5. global sea level rise without vertical land motion, but if you factor in vertical land motion for the point in Petone that the arrow is pointing to, it accelerates the amount of sea level rise. And you're getting the same amount of sea level rise much earlier than you would if you just considered global factors. And in this instance, I've highlighted 30 centimetres, and what you can see, I hope, is that it brings forward in time the amount that sea level will rise in Wellington Harbour by 30 centimetres. It brings it forward in time by 20 years. And from a planning perspective, that's a really important piece of information to have. And I want to emphasise that a lot of the presentations I've given around the country, around the world, people say, 30 centimetres, does it really matter? That doesn't seem like very much. What about, where they all get concerned about the high-end projections? But 30 centimetres matters. In Wellington Harbour, an increase of 30 centimetres in mean sea level turns what is today a low-frequency flooding event, something that might happen once every 100 years. That same flood will happen every year with just 30 centimetres of sea level rise. So don't wait for better projections. Adapt to the unavoidable now, but develop flexible plans so that you can consider the worst, right? So this message needs to be propagated. Don't wait, act now. I have a couple of images here. This is Catherine Mansfield's house. She's a very famous New Zealand author, lived in Wellington. She used to holiday in this house around Eastbourne, which is near the point on the previous map where the arrow was pointing to. She used to holiday in the 1900s in this house, and in 2013 that house was wiped out. And these events are happening only more frequently, and as sea level rises again, that 1 in 100 year event becomes an annual event with just 30 centimetres of sea level rise. Now, our local planners, our local communities are taking this information into consideration, and I found this image of Mr. Wave, who is directing traffic around the Eastbourne Harbour as construction has continued to build the seawall to protect where Catherine Mansfield's holiday house no longer exists from future events. So people are responding to the information we're producing, possibly not in the best way by building hard infrastructure, but at least they have the science to help guide their decisions. So the point I guess I'm trying to make here is that the ice sheet work that we've done, combined with vertical land motion, has been incorporated in New Zealand into our coastal guidance. So the updated sea level projections we've produced are linked to our updated coastal guidance. They are available for planners to consider, and there's some very clear guidance on how you can use that information. Not only at the central government level, but at the local government level, the Thames Coromandel District Council have produced some plans that include our sea level projections, but also provide a dynamic adaptive approach to sea level rise. So they're saying there's still uncertainty. You've got to consider things like high-end sea level projections. You've got to consider vertical land motion. There's a lot of uncertainty, so design your plans in a dynamic or flexible way, and they've laid that out here for this community. And you can actually see they're referring to the www.searise.nz. So this is really showing we are getting from science all the way through to planning solutions at least. Now this is all very good and well. We did this a number of years ago, and we got a lot of feedback from end users, from people in the community, and we've taken on that feedback, and it's really important that we do this, right, as scientists. We listen to what our communities are saying back to us, what do they need us to do, and try to improve our approaches. And the big elephant in the room when we produced our last sea level projections were earthquakes. What happens when we have a big earthquake? We got questions from people saying, yeah, but if sea level's rising, but then we have another earthquake, the land's going to pop up and we'll all be saved. And so what we did, this is kind of crazy, right? Hoping for this hope for an earthquake strategy. But anyway, we took it on board. But the challenge with earthquakes is that they don't always go up or down, and they're really hard to predict. And here's just an example of a couple of locations around the Wellington region. The east coast of the southern part of the North Island, there's a bunch of beach ridges that have been raised during past earthquakes, during large subduction earthquakes. Our data at the moment show that this region of the land is actually sinking at a fairly high rate because the subduction zone is pulling it down. Now, eventually there will be a large earthquake and land will pop up. And people think that might save Wellington. The problem is if the fault occurs on the Wellington's crustal fault, the actual basin will sink. So you've got this really challenging problem of geodynamics. But we've tried to incorporate what we can with respect to earthquakes, and here's an updated version of our sea level projections. The map on your bottom left here is highlighting the fact that we've now incorporated vertical land motion at high resolution all around the coast, so people can actually access these geodetic data in these maps, and we get a little bit less resolved as you move further inland. When you click on the projections now, you can see in this particular graph, it's steep to begin with up to about 2017, and then it flattens off. That's because at this particular location, the Kaikoura coastline popped up, and so we flatten off our projections because land is actually going up, slowing down sea level rise. But at some point, that uplift will revert to the pre-seismic event, and you start to see subsidence again, and you'll start to accelerate your sea level rise. So we're giving people the opportunity or the ability to actually play around with when that switch occurs. This is all beta. We haven't released this to the public yet. What we're also doing is trying to factor in the effect of erosion and working with coastal scientists who have techniques to actually look at how the coast will erode. And here's an example from the far south, working with Awaru-Arunaka near Bluff and New Zealand aluminium smelters down at Tiwai Point. And we're working to see just how the coastline will respond to sea level rise and the erosion effect of that sea level rise, wave energy and influence on the coast. And you can see with the two dashed lines in the bottom frame, the yellow line is the baseline for today, and the red line shows you the projections under SSP 4.5 by 2100 to include erosion. Again, this is all beta at the moment. And one of the key points is that when we do this, we want to test it with our end users to see whether it's useful. You know, is being able to turn on and turn off or switch back to interseismic rates, is that actually helpful, or is that just more confusing? And we had an opportunity to test some of this with end users at the recent Adaptation Futures Conference in Christchurch late last year. Got a lot of feedback from people, but we're actually going out and holding a range of stakeholder meetings, a range of end user meetings, involve ourselves in the community before we go public with this information, so that we're delivering the best product to help produce the best solutions that we possibly can. Now, I've talked a lot about central government and regional governments, but it also really matters to get down to local community level. And I've got a photograph here with several of our team members who are in the room today, Awhina Ngātwiri, Mawera Karatai and Tūmanako McLeod, and we've been working with groups, local community groups, based on a response to a request, right? They're coming to us and saying, hey, we really want you to help us out if we can. Now I'm going to focus on some of Awhina's work. Awhina lives at Whareroa Marae in Tauranga, Moana, about 400 kilometres to the north of us here. And Whareroa Marae sits between, or sandwiched between, the port of Tauranga and Tauranga Airport. Now it's really close to sea level, and there's not a lot of room to move, right, in terms of managed retreat. So Awhina's PhD research is focusing on using the best available science, mātauranga held by her whānau, rangatira and tupuna, and mechanisms to develop flexible plans for an uncertain future. And so this is really about bringing science and knowledge to develop solutions. And this work is super urgent. About a month or so ago, an atmospheric river system brought a lot of rainfall down to the northern parts of New Zealand, and with tragic consequences for the people of Tauranga. There were several deaths as a result of a landslide. But the frequency of these events are projected to increase. And as a result of this large rainfall event, Whareroa Marae was flooded. Now, with sea level rise and increasing frequency of these events, this flooding is going to only occur more frequently. So you've got cascading hazards, not just inundation from the coast, but you've got flooding issues, you've got landslide issues up the coast. So We're really trying to bring all of the science together, all of the knowledge from the different components of the Earth system together with local knowledge to prepare our solutions for the future. This is my last slide. It's just an attempt to summarize some of the key points I've tried to make during this talk. Bottom line is we've got to stop kicking the can down the road, right? We all know this, but we keep doing it. Early warnings, we keep talking about early warnings. Early warnings came in 1972. Papers that were released saying that West Antarctic ice sheet's going to melt, sea level's going to rise. We've known for a long time what we have to do, but we're still struggling, and I get angry, right? We've got to work hard to develop effective ways to communicate our science. Graphs don't always work. Continue our work to reduce the uncertainties, that's a clear one. Small amounts of sea level rise matter. Don't get fixated on the high-end storylines. They do matter, but let's just get on with what we know we can't avoid. Think local, build relationships, connect across a range of scales, prioritize connections with people that want to know, right? There are lots of communities that just keeps wanting to stick their heads in the sand. Why bother wasting our efforts working with them? Work with people who want to know, show the examples so that others start to follow. Adapt to the unavoidable while we continue to mitigate the worst. And again, those 2 points that came out of a session a number of days ago, we're committed to ice sheet loss, let's get on with it. High scenario dependence, let's mitigate. Ka pai, nō reira, tēnā koutou, tēnā koutou, tēnā koutou katoa.
Many thanks, Richard. So our next speaker is Rob DeConto, and he will talk about mechanism of ice sheet instabilities.
Well, that was inspiring, Rich. I worked in some of those same regional policy spaces that Rich does, and I think what you're going to see is that I feel like what I'm doing right now is adding to the problem, not so much the solution. But I wanted to sort of rekindle the discussions about brittle processes in ice sheets as being something that we really need to dig down and understand better. So you don't see marine ice cliff instability, the MICI acronym in this title. I'm feeling what it's like to not go there. But I wanted to be a little bit provocative today regardless. I think we can all agree that ice flowing to the ocean usually ends up in a cliff, regardless of whether or not it's the edge of an ice shelf, a smaller tidewater glacier, or something much bigger. The systems that we're going to be talking about today mostly are systems like this. This is Jakobshavn or Ilulissat in western Greenland. So this is a glacier that lost its ice shelf in the 1990s, and it did two things. It began to flow a lot faster toward the ocean, and it began to produce icebergs at an even faster pace, and you'll see an image of that in a minute. So the sort of requisite for most of what we're going to be thinking about today, and I just want you to start to try to form this image in your head. This is places where really thick ice is flowing to the ocean, terminating in the ocean. We're talking like order maybe 1,000-meter thick ice. Glaciers like Ilulissat, you can see really heavily damaged, heavily crevassed. We're going to, for the most part, assume that the terminus of these systems are pretty close to flotation. So roughly 1,000-meter thick marine terminating glacier producing roughly 100 or so meter cliff face. This is another really nice example. This is Helheim Glacier, and you're going to see a few more images of these systems. Okay, so this is what Ilulissat used to look like in the late 1980s and early 90s. It has lost its sort of stubby ice tongue, and this is what happened. It sped up. This is what it looks like today. And even though this is a relatively narrow fjord, there's a ton of melange, these broken pieces of iceberg, sometimes coalescing with sea ice in the winter. That actually slows down the pace of calving during the winter. But overall, even though the glacier is sped up, you can see this is the southern limb of Ilulissat. The glacier is retreating into the deeper, thicker ice of the more interior ice sheet. A couple of really nice, these are just Google Earth images. These are from last summer. There's Helheim. This is Kangerlussuaq. Kangerlussuaq produced incredibly rapid calving rates after it lost its buttressing supporting ice tongue in 2004. It's actually hard to pick out where the terminus is. You can see that it's almost sort of falling apart and slumping. You can see water on the surface. You can see water on the surface of Helheim. Helheim's famous for those full thickness, super dramatic, bottom out calving events that you've probably all seen really cool videos and images of. But that's not the only mode of calving, even in this one glacier. Here you can see a piece of ice with its series of seracs still intact. So clearly this piece was not part of one of those big full thickness rollover events, but a piece that probably a place where the terminus was beginning to float and that piece just broke away. So the point is that there are many modes that ice can fail in these systems, which makes it really difficult to come up with a universal sort of calving law, if you will, that we can put into a continental scale model to say something about what might happen in the future. And if you're interested in learning a little bit more, if you don't study this kind of thing, we wrote a review paper a couple of years ago, 2 years ago, that might be helpful. So for the most part today, I'm going to be pretty agnostic about the details of the style of calving that is happening because it's complex and it's different for every glacier and even parts of different glaciers. So back in 2012, Jeremy Bassis and Catherine Walker wrote it's a really cool paper if you've never read it, because it's so beautifully simple. All Jeremy really did was he looked at the stress balance at the edge of a glacier that's terminating in water, just like we've been talking about. And what Jeremy really clearly points out is that assuming that the terminus of this system is pretty close to flotation, the water pressure from the water in front of the terminus that provides a back force, or a buttressing, if you will, in front of that glacier is overcome by the glaciostatic pressure if you look at this in a depth integrated sense. And that produces a net longitudinal stress on the system. And all Jeremy thought was, well, if that stress exceeds some assumption about the material cohesive yield strength of the ice in sort of a more Coulomb approach way of thinking about this, that ice front is going to fail. It could fail through surface and basal crevasses just connecting and a piece breaking off. It could fail through basal and surface crevasses connecting through shear. It could be shear sort of connecting a surface crevasse to the free surface of the ice, sort of at the air-water interface. But the point is that you start to run against the limit of the strength of ice at scales of ice thicknesses and cliff heights that are pretty close to what we see in nature, around 1,000-meter thick piece of ice. Now, of course, there are big uncertainties about where that limit is that are very dependent on the assumptions about the strength of real glacial ice, how damaged it is. These systems are accumulating damage as they flow from the interior of an ice sheet out toward the ocean. Again, this is Helheim with its really amazing melange field. And even though there's an incredible melange field in front of that calving face, it's still calving at an extraordinary rate. So what Richard Alley and Dave Pollard and I, back in the round 2015 or so, tried to account for this kind of calving in a continental scale ice sheet model. And what we did was we used sort of the approach of Jeremy's, where we diagnosed the stress state at every little grid cell where the ice sheet is terminating in the ocean, and say, okay, it looks like we're beginning to exceed some assumption about the strength of the ice, and it's going to start to yield one way or another. And that represents this critical cliff height threshold, which is really a stress threshold. But you can swap cliff height, as you'll see again in a minute, with stress. And then we thought, well, if the edge of that ice starts to break and you start to go back into deeper and thicker ice, and the cliff is getting bigger and bigger and bigger after each calving event, perhaps that increase in stress is going to drive even faster failure. And at some point, we thought, well, where does this end? Well, maybe it ends where we observe calving rates maxing out in Greenland today, even though we were using systems in fjords supported by the walls of the fjord to some degree, supported by a lot of melange that sometimes freezes up in the winter, that slows down calving. We thought we're gonna be conservative and limit the rate of calving to what we observe in Greenland today. So you can see it's a linear calving law with increasing stress, and that's gonna be key in a minute. And this is what happened, right? Our ice sheet model projections without these processes were predicting that Antarctica would contribute, well, in East Antarctica, a negative sea level contribution, and we've heard a lot this week about additional snowfall and a warming climate on East Antarctica, and we were getting the same sort of result with some retreat in West Antarctica, mostly driven by the viscous processes, the so-called marine ice sheet instability. But with these processes included, you know, we went, wow, we're getting multi-meter sea level contribution over a few centuries. And this is really, in a sense, you can think of this as just saying, what if Antarctic outlet glaciers that have lost, remember the key is the loss of buttressing, the loss of an ice shelf or the loss of an ice tongue, if Antarctic systems start to lose their buttressing support and they start to behave like what we see in Greenland, this is what you get. So that doesn't really seem all that crazy of an assumption to me, but it has been perceived that way in some circles. What did happen, which I was so, you know, this is really, you know, thinking someday I'll be looking back on my career, this has been really cool. This has sparked a lot of new literature in trying to dig into this with mixed results. I think that, you know, most glaciologists understand the physics and that this is something that deserves some study. But, you know, what we're seeing are papers like this that actually published sort of in the front end of the paper that an ice cliff could be 500 meters tall and still be stable and not fail and fall apart. But if you change your assumptions about the material strength of the ice properties, that number comes down from 500 to like 60. Okay, so huge amount of uncertainty. So this still is something that we need to continue to work on. Now, really importantly, this is really a cool flowline model result of Jeremy Bassis has a model that blends different rheologies of ice, one for the viscous flow behavior of the ice and one for brittle failure. And I love this animation because this was kind of like what we always had in the back of our mind about what this process might look like. For systems, you know, what we're really trying to do is try to think about what we see in Greenland means about even thicker marine terminating ice reaching the ocean without any buttressing. And this is what Jeremy's simulations sort of look like. The first piece breaks and then it just keeps going and going and going. But what Jeremy found, importantly, was that if the ice doesn't thicken fast enough as you go upstream, after those first few pieces break off, there's a viscous relaxation at the ice front, and the ice front gets thinner, and the ice cliff gets smaller, and now you don't have the stresses you need to make the fracture happen. So, okay, maybe this isn't a true instability, maybe it's very conditional on the geometry of these systems, and that was a really important result. Okay, now, this is a great natural experiment. When the Larsen B broke up in 2002, it released the buttressing of the Crane Glacier, which is one of the tributaries flowing and coalescing into to make the Larsen B that used to be out here. The relaxation in the buttressing let the glacier's flow speed up, so the combination of the deformation and the sliding increased by a factor of 3, right, which is kind of incredible. And it was thinning, but what we're assuming is pretty close to the grounding line, retreated backwards by more than 10 kilometers in just 2 years between 2004 and 2002. So this is a really important clue. It means that the brittle processes can indeed outpace the ductile or the viscous processes. And that makes sense, because if we're assuming that creep is proportional to the stress to some power, maybe it's 3, maybe it's probably closer to 4, the community is thinking now, maybe it's as high as 5. But regardless, the propagation of subcritical cracks scales to something like the 13th power of the stress. Okay, now, Anna Crawford and Doug Ben and others utilized the Helsinki discrete element model. This is actually, something's happening in the animation. You'll see it unfolding here in a minute. It's going to look a lot like a Helheim-style bottom-out calving event. You can see we're using particles that have some cohesive strength together. You can tune that strength to try to get a system like this to mimic a real glacier. They ran a lot of different simulations with thicknesses, a range of ice geometries, and what they came up with was a fit to their model results using that kind of a model to propose some calving laws. This one is for a pretty stiff cold ice. This is for warmer ice, maybe more appropriate for Greenland sort of ice temperatures. And what they suggested was it looks, based on that particle element model, that calving would begin at stresses that would be generated by ice cliffs about 135 meters tall, and then increasing. You can see it's a power law dependency with a really tiny prefactor and a really big exponent, more than 7. So power law dependence. And they recommend, they made a suggestion that maybe this would be useful in a continental scale model as a way to parameterize marine ice cliff instability. Okay, Matthew Morligam picked up on that, and he put this parameterization into 3 different ice sheet models, centered, mostly concentrating on the Amundsen Sea embayment region of West Antarctica to see what would happen if this did anything. And what Matthew found was that for the modern Thwaites Glacier, the ice isn't thick enough to produce cliffs that get into this pink range, which is that 135 meter in higher range, so that the new parameterization didn't have much of an impact on Thwaites. And then Matthew thought, well, we're going to let the grounding line retreat back into deeper bedrock to see if this really does something. And you can see that more of the grounding line in at least one of these models is pretty deep into the range of ice cliffs that should make something exciting happen. But what Matthew found was you're still sort of down here in this range, or this power law dependency, so the calving rates are still fairly low. In the dynamic thinning, because there's no buttressing, Matthew and his colleagues removed ice shelves, so there's no buttressing. The ice thinned and moved sort of back off of these calving rates. So sort of, yes, it starts, but then the ice thins, and then you can move back off. And so nothing really dramatic happened. And based on these results, he totally rightly concluded that maybe this marine ice sheet instability isn't so important to West Antarctica. This is the caveat. These are the calving laws that came out of the discrete element models. These are observed calving rates from real glacial systems. And you can see that the smaller ones, with the thinner glaciers with shorter cliffs, lower rates, thicker ice, taller cliffs, faster rates, sort of looking somewhat like a power law dependency. But you can see that they don't really relate to reality. And that is kind of troubling to me, because the discrete element model simulations used a range of ice thicknesses that are within, what the Greenland scale of glaciers. Okay, so what gives? And what I think gives is that this is a real glacier. These are the initial conditions in the discrete element model results that produce those calving rates. Do you see crevasses? Nope. So, what I've been thinking about is that what might be missing is this. So here are two glacier profiles. This one has no pre-existing crevassing. This is the increasing glaciostatic pressure with depth. Here, the hydrostatic. There's a peak in the imbalance and the deviatoric stress near the waterline in the system. But if there's crevassing, you're going to intensify the stress between the crevasses because you're eroding the column of ice that's having to hold up the glacier. So there's stress intensification. So what's really kind of wild, and this is pretty much to scale, these two glaciers have the same end glacial stress, but this one has crevasses. And you can see that, well, this is a much smaller cliff than this one, and it's a much thinner glacier. So it's made me start thinking about this system as this sort of being an effective cliff height where these two systems are in a roughly equivalent stress state. This one just happens to be crevassed. So now, if you take a glacier system, you add crevassing based on the deviatoric stress, and then think about the possibility of increasing the surface crevasse penetration due to surface meltwater, you can start to think about something like this, where this would be an observed cliff height. This would be the cliff height with the same equivalent stress, but if the ice was undamaged, uncrevassed, and with strong material properties. And what you find is that with just dry crevassing, which is this dark line, so no meltwater influence on the surface crevasses, a 100-meter tall cliff produces the equivalent stress of an uncrevassed cliff that is about 200 meters tall. So adjusting for this effect of just taking into account the effect of buttressing, crevassing, the additional influence of meltwater production on the surface, driving surface crevasses even deeper, and looking to see what the end glacial stress state does, what we find is that the first thing that happens is this is the original Crawford et al. Calving rate curve from the discrete element model. Accounting for crevassing, just dry crevassing moves from the red curve way over to the left, to the blue. This is the observed calving rates at Jakobshavn. And you can see we're pretty close actually now to be able to match observed calving rates for a system this size. We can run a large ensemble where we play with the sensitivity of the surface crevassing to meltwater and come up with a best fit in the model, which is shown right here. So here's a calving law that fits Jakobshavn. It's still based on the discrete element model power law dependency on calving rate, but it fits observations. We can do the same thing for a different glacier, Kangerlussuaq, get a perfect fit. Same thing for Crane Glacier during its really rapid retreat after the collapse of the Larsen B. So now we have a calving model that works in a range of systems with different thicknesses, ice cliffs, meltwater production rates. It even works for Columbia Glacier during its rapid retreat in the 1980s. And now, just to wrap up, I'm going to show you what happens when we apply this new model to future projections. Oh, the other thing that we do, I just want to stress, that when we put this new code into the model, it still does a really nice job with the modern ice sheet, doesn't degrade the simulations of the modern ice sheet. It actually improves our matches with paleo, sea level estimate contributions from Antarctica. So right now, I would have no reason of discounting this new model. Okay, so now we're just going to look to see what happens in the future. We're going to do just a couple of different things. We're going to either have 2025 climatology as predicted by the NCAR CESM climate model with ocean temperatures from the same model. Or we're going to use the 2025 climatology and either warm things up by 2 degrees or 5 degrees, and we're going to see what happens. So this is without any additional warming beyond modern temperatures, so 2025 climate, and this is sort of getting to Rich's concern about commitment. You can see that there's a little chunk there of waste going away. This is in 2300 with plus 2 degrees. That's 2300 with 5 degrees. And you can see just within a few centuries that most of waste is gone. Those are the hot spots, which is pretty interesting. It looks like there's a lot of ice being contributed in East Antarctica. Definitely Cook and Ninnis glaciers seem to be a hot spot, but most of the contributed sea level is from the Thwaites in interior West Antarctic basin. And 2 more slides. Now this is, again, so these years are going by pretty fast, but this is really deep, thick ice. That's Thwaites. And you saw a really rapid retreat, and it's because we got into ice that if there was a calving front there, it would have cliffs that would get you on the really steep part of that power law dependency in the calving rate. And this is what things look like in terms of the long term. And this is my last slide before the conclusions, but I'm assuming this would be of interest. What's interesting, so this is the old model that resulted in some ways in that famous dashed red line that we saw in a couple of slides this week of the IPCCs versus the new model. The new model's in blue, old model, calving model with the linear calving law is in red. And you can see that under low emissions, the new approach is producing more sea level rise, but not that much more, okay? So this is the cumulative sea level rise. This is the rate of sea level rise, and it's really spiky. And so even if the background sea level rise isn't rising that much, the rate would be really challenging in terms of thinking about the limits of adaptation. But under really extreme warning scenarios, the new model is producing quite a bit less sea level rise, which is encouraging than the previous model did. But it is this spikiness that is of some concern, thinking about adaptation and just the issues that Rich was just talking about. So in summary, thinking about this, we might be onto something with a new representation, parameterization of calving that is applicable to continental scale ice sheet models. By the way, the simulation that you saw with the really rapid retreat, that was a 1,000 meter resolution simulation, so high resolution. We're doing a good job with modern glacier systems, with paleo. I would say the outlook for Thwaites doesn't look good, even with sort of current atmosphere and ocean temperatures. This is a big question. What would be the role of melange, especially when you get into those really rapid rates of ice loss, potentially providing enough buttressing to slow things down? We don't think so in an abatement as wide as Thwaites based on some new model results that I'm not going to show here today. Calving remains a huge source of uncertainty. Its representation in the continental scale models we need to do a better job with. And I really hope that, I was so encouraged by Daniel Richards' talk, I don't know if anybody saw it, that there are folks that are working on trying to get at the processes that will potentially allow us to scale up to parameterizations that we can use to improve the predictions and to reduce the uncertainties. Thank you.
Thank you very much, Rob. So our last speaker now is Professor Shin Sugiyama that will talk about research about climate change in Greenland with local communities.
Good morning, everyone. I'm Shin Sugiyama from Hokkaido University, Japan. And today I'm very glad to present our study on climate and environmental change in Greenland with local community. So this is a kind of my experience over the last 15 years, somewhere in between the science and solutions in this small village, Kanak, in northwestern Greenland. So we have been working on glaciers and ocean and other environment in the small village, Kanak, in northwestern Greenland since 2012. And we started our research with glaciers and ice sheet. And then we went to ocean and land systems. And more recently, we are expanding our research into the tradition and more so society-related issues. So today I want to tell you the story why this happened to me. I'm a glaciologist from glacial research, but now I'm doing waste management in Kanak. So this is our study site, northwestern Greenland, and land are covered by Greenland ice sheet and separated ice caps, and this is the location of Kanak, the village with 600 people living. And I study glaciers, so this is my usual business, sitting on snow and ice, measuring the height of the stake to measure mass balance. This is very simple but important measurement for glacial research. And 15 years ago, it was already clear the change was happening. The glacier was darkening, and ice caps are thinning at a rate, let's say, 1 meter per year. So this was my first year in Kanak. And next year, the second year, we went for carving glaciers. In these regions, a number of fast-flowing outlet glaciers are flowing to the ocean. So we took one of the glaciers, Bowdoin, and these types of glaciers ending in the ocean is rapidly changing than land-terminating glaciers with interaction with the ocean. And we spent a lot of time on this glacier and found the change was more rapid than land-terminating glaciers. In this glacier, every year, 5 meters of ice was missing. And I tell you, until this moment, we are just us. We are on the glacier. We used airplane, helicopter, but we didn't have a lot of interaction with people living there. But as soon as I started work on this environment, we are on the glacier, but this glacier is really affecting the ocean by discharging meltwater, iceberg, and sediment. So I started to think about we should study this ocean. And the change happened to us at this time because we needed a boat. So we asked local hunters if they can help us for ocean measurement. So this is a local hunter, and she helped us with her boat. And what we did with her boat is, for example, the ocean depth measurement. This is quite important for the change in calving glaciers, like Rob mentioned in this talk. And when we did this with hunters, I'm surprised how the hunters' interest in this data, this depth of field, because it's very important information for the fishing of halibut. Halibut is very important catch in this region. In wintertime, they drill a hole in sea ice and they catch a lot of halibut. And to do this, they should know how deep the fjord is, because halibut lives only some certain depths of the ocean. So they wanted to know more about ocean depth distribution. So we decided maybe we can leave our instruments on their boat. So my younger colleague is working with the hunter to tell them how to install and how to operate the instrument. So the next year when we met them, they started their own measurement. So they got data wherever, and these are places I have never been, but we know the water depth from the measurement. So this is an interesting moment. The science is not only for us, not only for science, but something connected to their life. And with this environment, what we found, one of the things what we found is the marine biology in front of calving glaciers. Near the front of the glaciers, the meltwater discharge upwells, and this upwelling plume provide a lot of nutrient and plankton to the surface of the fjord, and a lot of fish, birds, and marine mammals are coming to the glacier front. And we thought we discovered this, but actually the hunters on the boat, oh, this is already known. So it was only scientists who didn't know this. Everyone knew about this, because it's a tradition to hunt marine mammals, the seals, whales, so they have already known how they behave and where they go to hunt the seals. So we spent a lot of time with them on board, talking about seals, glaciers, ocean, and we realized now we can do much more than we did alone. And one example is, this is narwhal, endemic animal in Arctic, and hunting narwhal is the tradition in Kanak. And narwhal is very sensitive animal, so it's very difficult to approach and difficult to study. But with these experienced hunters, we can go with their boat and approach and throw the microphone into the water. So this is the voice of narwhals, so that we can listen to their voice, what they are telling each other in the water. This we couldn't do without their help. And another approach, another young colleague started to talk to the hunters if they can give her stomach of seals and whales, because stomach is not useful for them. So they throw it to dogs. So before it goes to dog, she collected in a plastic bag. And over 2 years, she collected nearly 100 stomachs of 3 kinds of seals and narwhal, so that they can investigate what they eat. She invited local young researchers to accelerate the analysis, and she found what they eat, seals and whales. And interestingly, some of the fish and plankton, they are not familiar in that region. So seemingly, the ocean is changing, and many species are migrating from south to north. So this is an interesting result. And I'm from Japan. The people are very critical about this kind of animals. So that's exactly what we are seeing in our country. I'm living in the northern island, Hokkaido, and people are happy about increasing amount of catch of this big fish migrating to north because of the ocean temperature change. But on the other hand, we are missing some other animals which are very common, but now it's very few. And it's not only marine animals. So this region is famous for this little oak key seabird in the Arctic. And this region, they hunt like this. So he catch, let's say, 100 birds within 1-2 hours. And it directly go to my colleague before they send it to kitchen, so that they can collect the feather to study the possible contamination of heavy metal and plastic in birds. So Kanak is at 77 degrees north, and only 600 people are living there. And I spent a relatively long time there, every year, maybe 1 month. And I realized the life in Kanak is pretty much influenced by the Arctic environment. So this is the photograph in July, the midsummer in Northern Hemisphere. And this is the time the first supply ship arrives in that year. So the sea ice stays until the beginning of July. So mid-July is the first ship since the last ship came October last year. So people are waiting for things for supermarket, and people ordered big television by Amazon, but it arrives only with this ship. So is it a good thing if sea ice melt earlier so that they can catch their things earlier? But on the other hand, the dog sledge is still used in this region. It's important means for transport, especially for hunting. And now the weakening sea ice causes a lot of troubles, and sometimes dogs and sledge are drifting away from broken sea ice. And we also see more direct impact of changing climate on the life. This is 2016, when we are there, a lot of rain for 2 days. And the rain is not so common in this latitude. And heavy rain is clearly increasing in this region. And this is the river destroying the bridge in the village. But at the same time, this is an important road connecting village to your right and airport to your left. And this key infrastructure was destroyed, and it was so difficult for transport. Because I have a flight on the next day, so they decided to operate helicopter from village to airport for 3 kilometers. So I took my photograph from this helicopter for my flight. So we started our measurement for river discharge together with our measurement on ice cap, behind this ice cap and glaciers. So this is together with rainwater and glacier melt. So according to our study, we can say this kind of discharge from the glacier is 3 times more after 4 degrees C warming, which is projected by 2100. And it's not only river flood. That heavy rain caused the landslide on the steep terrain behind the village, and some buildings was destroyed. So I have nothing to do with landslide, but luckily I had a colleague who can deal with this, with in-situ measurement and satellite data. They can create a kind of hazard map to project what happens in the future. So our study is getting closer and closer to the society. So we decided to inform the people what we are doing and what we found from our research. So this was 2016, the first, we call it workshop with local residents to explain what we are doing. And first I thought I can talk to the people, what we found, what we have. But actually, the people are very talkative. They started to talk a lot ask questions, and they started to speak about what they know about change in the nature. So we started to share our data, and they told us their story, knowledge, wisdom. So this is an excellent opportunity to talk about what we can study the next, what is important for the region. So one example is our most recent research topic is here. So this is Kanak, 600 people living, and about 1 kilometer from the village and close to the coast, there's a dump site. And I would say every small village in Greenland, and probably it's not only Greenland, many villages in the Arctic, it's like this. They don't have capacity to properly deal with this thing, and they don't have ship to carry out from the village. So it's there like this. So people worry about this because it's very close to the ocean. So if something going out from this, it's a problem. So they somehow requested us if we can do something with this. So I talked to my colleague in the university and started sampling of soil and water. And this is the concentration of lead in soil and water. And this marker size is the concentration. And if you look at this yellow dot, this is the upper limit standard in Japan. So the situation is not very good. And a lot of water is flowing out from the dump site to the ocean. So as soon as we got this result, we shared the result with the people, and especially hunters concerned about this, because they rely on the resources in the ocean. So we started conversation how we can work on this. So now we get help of hunters to collect small samples to investigate if there is any influence of this pollution to the ocean. So now I want to ask myself why I do this. I work with the local community, and I have several answers to this question. First, I feel it's fair to tell them what we are doing, because imagine if someone, foreigner, comes to your town and doing GPS measurement and sampling, I feel not okay. So it's fair to tell them what we are doing. I think it's fair, and also we are very comfortable after talking to them. We are very comfortable about our activity in the region. So this is the first reason. And we can do much better science. Many things we couldn't do without help. And they tell us which direction we should go. They tell us what is important, what is urgent. And also we can learn a lot for our own life. The fish is changing. Oh, it's the same in Japan. So we can exchange our ideas and experience. So this thing I never thought about 15 years ago. So we are lucky about the funding. So this research was operated under a relatively large Japanese Arctic research project. Somehow we got funding every 5 years. It was green, ARCS, ARCS2, and now it's a fourth phase called ARCS3. So the next 5 years, we continue this work in Kanak. Okay, so it's already 15 years, and I feel we are very slow. It's a very slow step, but I think it's important, even slowly, we should step forward with the local community for this kind of issue. Thank you very much for listening.
Okay, many thanks for listening to those great talks, actually. I mean, to me, it's truly inspirational. I mean, especially the science to solution. Not that I'm bored with ice physics, but well, I really particularly appreciated the last talk. I think it's very different from what I am used to do. So, actually, I have put out some few questions just to challenge a little bit everyone on the concept. So the first question I would like to ask everyone, actually, so you can answer all one after the other, is, so among the changes that we can already observe in the glaciers or ice sheets, which one are mature enough to be actionable and functional as early warnings for decision making?
Thank you. Because I study glaciers, and I go to glaciers in Switzerland, Greenland, Alaska, Patagonia, and what I see the most evident is a change near the glacier front. Glacier is retreating and thinning the most near the glacier front. So many things like lake outburst flood, and also the unstable, the steep terrain after the glacial retreat. And these are, I think, convincing enough for the people that we should do something for this.
Yeah, I pretty much agree. I mean, I was thinking, what's the most confronting to me and most obvious? It's the really clear changes in glaciers, right? There's so much documentation. That's a really clear early warning. In terms of sea level is rising, has risen 20 centimetres. We know that from the observations, from the measurements, and it's not slowing down, it's accelerating. So that's a pretty clear early warning to me. I guess I was chatting to Rob yesterday and we were sort of wondering, well, how many signals and signs do we really need before we act? And I guess we just need to promote the message that we've been warned. We don't need to wait for the next warning or the next signal. It's happening now, let's act.
Yeah, I totally agree with your opinion about early warning signals. Talk about Tibetan Plateau and the surroundings. The most warning signal is ice caps. Before 2016, we have any knowledge about ice caps in the region. And in 2016, the largest ice caps occurred in the interior of the Tibetan Plateau. And that event caused life of up to 10 or so, and animals, and livestock, and grass, and the very serious damage. And after that, we had ice caps in 2018 in southeastern Tibetan Plateau, which damaged the local heritage and also damaged the Yangluzangbu, the operators of the Brahma Pucho. And then we have 2020 ice caps in India, South Himalaya, caused 200 people's lives. So that is really a serious signal of what is happening from glacial melt.
So for me, I think regarding the ice sheets, it's all about the shelves in Antarctica. So one thing I didn't say, if the ice shelves disappear, the edge of the ice sheet cannot just break like I was focusing on. It flows faster, and now we know there was a really amazing intercomparison using ice sheet models where you just remove all the ice shelves and see how fast you can deliver ice to the ocean. And those simulations produce the sort of magnitude of sea level rise that I just showed with the fracturing. So it's really about the ice shelves, and we're witnessing them thinning. As they begin to thin enough to lift off of places that they're maybe bumping into some bedrock topography, they're providing less of that support for the edge of the ice sheet. So that to me is an important early warning system. And the role of meltwater. The ice shelves are flat, they're at sea level, and someday it's going to be warm enough, so they're going to start to become flooded with water in the summer. And I think when that happens, and we start to see that happen, I would probably sell your beach house.
Thank you very much. I see that we have a number of questions that have popped up, actually. So I think we will take some. But before taking the one that have been pushed through the application, I would like to ask if there is John Howell in the room this morning. Tim, is your neighbors here? No? Okay, because you had an interesting question. So I will read it, and then you can decide who can just take it, okay? So it says, in her presentation on crisis, Petra Heil wrote, a holistic system-based approach is now required to address knowledge gaps, leveraging bespoke international capabilities, and an integrating strategy to observe and assess the polar system. Nicholas Golage explored the evidential basis underpinning interferences of ice sheet reorganizations and highlighted how approaches borrowed from dynamical systems theory can illustrate and quantify long-term ice sheet evolution. I take from this we are dealing with a complex interacting set of variables in a dynamic system. I wonder, therefore, if the effort to identify tipping points is the wrong question to ask. If we use analogy of the health and fitness of the human body, because I think he's a biologist originally. There are key indicators, but the physician is watching the parameters of homeostasis and how this changes with age and circumstances. For example, a disabled person may still be fit and healthy because other capabilities are developed. Therefore, instead of tipping points, would it be better to develop a cluster of indicators to warn the degree of particular stresses to planetary or regional boundaries?
I want to ask you, what do you think? I want to repeat this question to you.
Flo, can you put that in one sentence?
In one sentence. So, instead of tipping points, would it be better to develop a cluster of indicators to warn the degree of particular stresses to planetary or regional boundaries? So no tipping point, no thresholds, but a range of indicators that are less abrupt or perhaps like just show more smoother changes. I don't know.
I would say yes and yes. I mean, I think, so that, the tipping points concept, as I'm sure many of you know, has become somewhat controversial among our community. The IPCC has really latched onto it. It ultimately is derived from studies in social science. But I think some of the language has helped us in terms of communicating abruptness, non-linearities in systems to the general public. So I don't think we need to throw that away. At the same time, about thinking about complex interacting elements of those systems at the same time as being super complementary and very much part of the portfolio of things we need to be working on.
Okay, thank you very much, Rob. Okay, so let's have someone wants to add on this. No, that's okay. Okay. Okay, so let's proceed with another question. So, for you, which type of urgency is most effective for adaptation? Urgency driven by observed impacts, or by projected thresholds, or by social vulnerability?
I think it depends where you ask that question. If you are asking this, for example, the region directly impacted by the change of the climate. So, of course, what is happening, the hazard or things, this risk is the best thing to convince the people. But if you are living in other places, no glaciers, no ice sheet, and not much seeing, it doesn't make sense to the glacier is melting just like this. So we should tell them more global view and longer time scale, what we'll have in next 100 years, 200 years. This is more efficient, and those people should think about the things in that time scale.
Yeah. To me, it's all about the vulnerability, right? If you can observe a physical change and you go, okay, that's going to happen more frequently. If it doesn't actually have an impact on you, then it doesn't matter too much. So the vulnerability and exposure and the risk associated with the specific local situation, very much as you say, that's the most important thing, rather than getting fixated, I think, on future thresholds and projections. It's the immediate issue and the vulnerability and the exposure and related risk.
Yeah, I think for the Tibetan Plateau and the surroundings, the impact is quite influential, and you will see that from the changes of agriculture, and the people never cultivate corn before. Now they are cultivate corn, and you can see the train rain lines rising. It's everywhere in the southern Tibetan Plateau. You can see the grassland changing, which is now rising up to the very high altitude, and also the changes of life behavior. People wearing very thick clothes before, now just jacket. So people will tell you a story, what they experienced. So everywhere in the Tibetan Plateau.
Rob, would you like to add something? No, that's okay. Okay, perfect. Another questions now. I think from the floor, actually, was to Richard, but I think it can be also addressed by others if you want, though it's local. What coastal sea level rise adaptation and mitigation strategies have been implemented throughout vulnerable regions in Aotearoa?
Say that one more time, Flo.
What coastal sea level rise adaptation and mitigation strategies have been implemented throughout vulnerable regions in Aotearoa?
Not many and not enough yet, but there are examples, and I'm going to speak from a sea level perspective, where I was lucky enough to participate in a workshop at the recent Adaptation Futures conference run by Judy Lawrence, where there were presentations by communities where people are actually purchasing and acquiring land inland from the coast and starting to develop financing solutions so that you can start to purchase and afford the ability to migrate inland, and they're doing that well in advance of the need to do so. There are a few marae around the motu, around the country, that are also very actively developing plans to move away from areas they know that are highly exposed. So there are examples of communities, pretty much communities, taking action now, but they're few and far between. And of course, I tried to show some examples of some of our regional councils that are adopting a dynamic adaptive planning approach, which is an approach that, for those of you that might know, Marilyn Hasnut has been promoting with many others to try to accommodate uncertainty, because people don't want to lock themselves into solutions that are either expensive or not appropriate when there is so much uncertainty regarding the future. So we've got scattered examples of communities doing this around Aotearoa. But again, I think we've got to have around the world better connected, coordinated strategies to make sure that this is happening more broadly.
Thank you, Rich. A question to Rob now. So, how much actionable information can we retrieve from high-impact, low-confidence processes, given the associated deep uncertainties and long time scales?
So how did that begin?
How much actionable information can we retrieve from high-impact, low-confidence processes, given the associated deep uncertainty and long time scales?
So that's a very tough question. But I keep thinking back to the way that Richard posed this issue, that we need to plan for what we are pretty certain about, but keeping an understanding that there could be something way outside the likely range of our projections, and to begin to think about how to be adaptable to that magnitude of change. You know, this has been a tough messaging issue for the IPCC. So the IPCC AR6 report published projections of sea level rise. They had sort of their main set of projections, and then there was this dashed red line that I mentioned, trying to be cute during my talk, that was just based on 2 studies. But it was really just to drive home the fact that there could be outcomes outside of the likely range, you know, the 17th to 83rd percentile range, that has been coming out of models that don't include some of the processes like the ones that I talked about today in them. The problem was that they called it a low likelihood, high impact outcome or storyline. And the use of low likelihood on that figure basically drove a generation of policymakers and coastal planners to think that the IPCC was able to assess the likelihood and had determined it to be low. When in fact, the point of the message was that we don't know the likelihood. And that messaging has actually done enough damage so that I think in the AR7, the language is going to be adjusted to open up a different way of thinking about these potential outcomes.
Yeah, that's true. And now I have a question for Dr. Yao, Professor Yao, sorry. And I think Professor Sugiyama, you can also comment on that. So how can local and indigenous observations complement instrumental monitoring to minimize impacts from natural hazards and glaciers ice loss?
For the local people?
Yeah.
Local community. Yeah.
How can local indigenous observations complement instrumental monitoring?
Yeah, actually, that's one of our big objectives in the future. And we have done that before. We cooperate with managers in the counties. So they have different projects to observe the processes, like water, and also snow cover, and they even use the glacial meltwater with local way approaches with the ditches, and you use that to irrigate their agricultural activities, even for their family lives. They have ditches, they have the bamboo pipe, and to their families. So what we are doing is just to communicate with them. What will the water come? What will the period? This year, it's earlier, it's late, because usually now with the warming, the water is coming very early spring, but some period in the middle, no much water. So what you are doing is to coordinate with such kind of natural processes. And also one example I told you about mountaineers. There are mountaineers every year. We just train the mountaineers, and if they go there, just observe the processes at the extreme high elevations. So that's what we are doing, and we will further develop this kind of approach.
I see. Thank you. Yeah, you can comment on this. And well, to conclude, there is also a couple of questions from the floor that are also for you. So I just package everything so you can just comment on everything. So one is about if there have been some updates about the management of this waste problem since then in the community, and also about the long-term community engagement. How did you use a specific framework to get the community engaged with you, like in the research? So please.
Yeah, for this waste management issue, this is happening for the last 1-2 years. So now we got this data, and what we should do now is to go out of Kanak. There's no solution within the village. We need some action of the government. So now we are trying to go to Nuuk to explain what's happening there. So it's the next stage. And I never thought about such framework, how to work with the community. It's quite naturally, automatically happening to me. So I can't explain how I can do this. And may I add one more comment to Tandong's, this question about how useful is the local engineer's measurement. And what came up to my mind to this question is, during COVID, I couldn't go there for 2 years. And this simple measurement of glacier is very simple, but very important for us. And if we don't go there 1 year, it melts out and no measurement. But the local people, with help of local researchers, they continued the measurement for the COVID period. This is really complementary. They helped us. This is very simple answer. Then I thought about, is there any need for me to go there if they can do this measurement? And I'm flying with fuel, and I have a lot of waste, and which causes the problem of dump site. Does it make sense? That is coming into my mind. So I think the people should do on their measurement if it is possible, and it's better if people are responsible for their own environment, own risk, so that they can think about more global problems. Now I can't talk to the people in Kanak about global sea level rise. They are directly affected by the things happening there. So if they can study or they can monitor their own environment, I think they can co-work with for global things. That came up to my mind.
Okay. Thank you very much. And a last question before releasing everyone to the coffee break. So it's for Richard and Rob, actually. So, Richard, you mentioned already that during your talk, but so are we at risk of maladaptation by waiting for better projections? When communities need flexible strategy to adapt based on imperfect but timely results?
Again, I think that the answer is yes. We don't need to wait for better projections. Certainly, some of the stuff that Rob was showing in terms of when we might expect the rates to increase, timing matters, magnitude matters, but we can't sit around and wait for the next best projection to come out. People need to start adapting now, and that's a message we need as a community to propagate.
But how could you convince the local authority? I mean, if you go and how would you frame that?
Yes, I mean, I think just by getting involved, pretty much, that's how we're managing to do it, is to reach out to communicate what we know. Sort of what we're discussing here on the panel, show the examples of how things are changing, but also just ask the question, what are you seeing locally? Most people are seeing the impacts. That's why people are starting to more and more come to us. They're seeing the impacts of sea level rise now, so don't wait for future projections. You know things are changing. Get on with it, I think, seems to work with us. The more challenging action, I guess, is when people are thinking about large infrastructure, building very expensive solutions. They're wanting to know with more certainty what the future magnitude might be. And that gets a bit tricky, right? Trying to build seawalls around Singapore and invest $100 billion to do so. Building airports, hospitals, things that really cost a lot. They're wanting to know with more certainty what the future holds. And that's where you have to, again, try to bring in a flexible adaptation approach. That's where local monitoring becomes important. Pay attention to what's happening, set up monitoring networks so that you can see whether the rate is increasing or staying about the same, and then keep factoring that into your plans. Engineers hate that, but that's really one of the only ways to handle the uncertainty, particularly for the longer term.
Thanks, Richard. Rob?
Yeah, I would just add, and maybe this is something we can talk about over coffee, some things that we didn't touch on regarding adaptation are just, I think a lot about the climate justice implications of, for example, these huge potential sea levels in the future. In places that are very well resourced, we're beginning to see insurance in crisis, and where a few of the people in the room live in coastal New England, for example, that has become a real mounting issue. But I really think more broadly about the adaptation of financial systems and government policy around helping under-resourced communities that have done the least to cause these changes, that are on the front lines of dealing with the consequences that's happening now, and figuring out how we can actually adapt those financial instruments to You know, it's not just about the engineering. I'm sure we can come up with some really interesting ways where we can build infrastructure that is adaptable to a higher sea level, for example, without having to tear it down and rebuild it. But it's more the social, the financial side of things that I think we have a lot more work to do in figuring out from a sort of environmental justice lens.
Thank you very much. Thank you very much to the speaker. So a big round of applause to our courageous speaker.